Here's another example involving the rare event rule and the central limit theorem. A manufacturer claims they produce bolts with a mean thickness of 1 inch and a standard deviation of 0.25 inches. A customer takes a random sample of 100 bolts and finds that the mean of the sample is 1.04 inches. Should the manufacturer's claim that the bolts are 1 inch on average be rejected? Okay, so let's see what information we have here. We have the mean of the population as claimed by the manufacturer is 1.00 inches. We have the standard deviation, 0.25, and the customer is going to take a sample, or took a sample, of 100 bolts. So that's our sample size. Okay, first, does the central limit theorem apply? We don't have any information about the original population's distribution, but our sample size is well over 30, 100. Remember the criteria that if the sample size is greater than or equal to 30, then we don't have to worry about whether or not the original population was normally distributed. So, because we have such a large sample, yes, we may use the central limit theorem. Okay, so let's sketch, label, and shade our curve. Okay, and for our mean of the sample, the manufacturer's claim is that the population mean is 1. And so let me write that over here. But our mean let me write our sample mean is the same as the population mean. So the parameter for the sample means is the same as the population, right? And our standard deviation for the sample means is the same as the population standard deviation divided by the square root of n. So we have 0.25 over the square root of 100. Now, since 100 is a perfect square, we can rewrite that as 0.25 over 10, and then write that as 0.025. Now, if we can get a nice terminating decimal, that's fine to do. Otherwise, I recommend you keep the expression as it is and not make any changes to that, because you'll need a more accurate result. Don't do any rounding here. So we didn't have to do any rounding. So, okay. So now our z-scale, on the z-scale, our mean is 0. And what we're interested in is that the bolts they claim are on average 1 inch. So what we're interested in finding out is the probability that the bolts are larger than 1 inch or smaller than 1 inch significantly. So we could be here at 1.04, or we could be 0.04 away in this direction. They could actually be different in that direction. So 0.04 away from 1 in this direction would be 0.96. So we're just saying, is it exactly 1? Is the true population mean 1? Well, it could be higher, as they found in their sample. But again, it would not be 1 if it was also lower by the same amount. So we actually want to get the sum of these two areas. So we need z-scores for both of these values for our sample mean. Okay, let's do that calculation. And let me say that again. It just says, is the manufacturer's claim correct? We're not saying that it's we're claiming that it's actually higher. We're just saying it could be higher, could be lower. So we're looking at both tails here. Alright, so the z-score for 1.04, remember we take our sample mean minus our mean of the sample means, or population mean of the sample means, over the standard deviation. And this is 1.04. And we said that would be 1. And this, after running through the calculation, would be 0.025. Okay, and we get, running that calculation, 1.6. So our z-score here for 1.04 is 1.6. Now, we know that the standard normal curve is a symmetrical curve. Here's the center, the line of symmetry, and so the z-score for a value that is the same distance away from the mean would just be a negative, or the opposite of this number. So if this is 1.6, if we go 0.4 away in this direction, we would be at negative 1.6. So there's no need to run that calculation, although we could do that. If you run the calculation for putting in 0.96 right here, you'll end up with negative 1.6. Perhaps it's worth doing. If you run through this, we'll get negative 1.6. But I do want you to get the idea of the symmetry of the standard normal curve and how that can work for you and make things go a little easier and give you better understanding. Okay, so what are we trying to find here? Let's get this written up. We want the probability that our x bar is less than 0.96 or x bar is greater than 1.04. And I'm purposely using less than, greater than, less than or equal to, and other examples, greater than or equal to show you that it really doesn't matter, because remember, exact values have a probability of 0. Okay, so that's the same thing as saying the probability that our z is less than negative 1.6 or z is greater than 1.6. So what we'll do here, we'll have two areas to calculate, and I'm just going to actually write this with our notation. We'll do the normal CDF. It's not a bad idea to write this to help yourself understand what you're doing, to write all this down. Okay, I need from negative 5 all the way up to negative 1.6, from my low to my high. And I'm going to add that. Remember, or, the key word for or is addition, or the key word for the addition rule is or, but those two go together. So I know I'm taking the sum and normal CDF. Now my low value is 1.6 all the way to positive infinity, which we're using 5. Okay, so see, it's very clear now what I need to do. I've got it all lined up here, nice picture. I can tell where everything's coming from, and it's easy to follow what I'm doing. Okay, so let's run these calculations. Negative 5 to negative 1.6. Okay, normal CDF, negative 5 to negative 1.6. Okay, I get 0.054799. Now, ultimately, I plan to round to 4 decimal places, but I don't want to do that right now because I'd be introducing error. So I'm going to take it out to 6 and then round once I do the sum. Okay, so 0.054799. Now hopefully you're thinking, well, wouldn't the other area be exactly the same? Yes, of course it would, because this is a graph, the graph is symmetrical, and so we are the same distance away from the mean, and the area below that would also be the same as the area above that. So we'll be adding that, but let's just check it. Be sure we follow that. So now I want normal CDF. We're going to start at 1.6 and go all the way to positive infinity, or what we're calling positive infinity 5. Whoops, I hit the wrong one, didn't I? Well, that's good. You can see you get something that doesn't make any sense, gives me a chance to correct my error. I didn't tab down to the normal CDF. Let's try it again. From 1.6 to 5. Good way to catch your mistakes, to be aware of what this should be. And I have an idea of what it should be, 0.054799. Okay, same thing. And you could have just said 2 times this amount, right? That would have even been quicker from using your understanding of the normal curve, standard normal curve. Okay, when I add these together, 0.109598. Now it's time to round to 4 decimal places, 0.1096. Okay, so let's interpret our results. Okay, so there, the mean thickness of the bolts, if the mean thickness of the bolts is really 1 inch, as stated by the manufacturer, then there's a probability of .1096 or 10.96% chance, just another way to say that, of getting a sample mean with a sample size of 100 of, the sample mean would be 1.04, now let's say this, with a sample size of 100, we're getting a sample mean with a sample size of 100 as extreme, as 1.04 inches. So by that we mean it could be higher, as extreme as that, higher or lower, and that's what we tested. So let me make a note, 0.04 inches or more above, or 0.04 inches or more below. So measuring out that extremeness, 0.04, that's a 0.04 inches or more above, or above that mean, or 0.04 inches or more below. So using the cutoff criteria of 0.05, we find that the sample mean is not unusual, because we have 0.1096. So, in other words, there's a 10.96% chance that a randomly selected sample of 100 bolts would have a mean thickness above 1.04 inches or below 0.96 inches. So thus we conclude that the manufacturer's claim, which was our assumption, he claimed 1 inch exactly, his claim that the mean bolt thickness is 1 inch should probably not be rejected. So let me make that note. The manufacturer's claim should not be rejected. At least based on this sample, we did not find any reason to think that if you go pull 100 bolts randomly and get their mean, measure their mean thickness, that it would be 1.04. That doesn't lead us, that there's a 10%, almost 11% chance of that happening. So that's not unusual considering a 1 inch population. Okay? All right. That concludes our second example.